Okay, this lecture covers the image construction associated with a plane mirror. It uses the law of reflection. Okay, the diagram that I am about to draw is the first example of what is called a ray diagram. You are going to be expected to know how to draw ray diagrams for various topics that will be covered from this point going forwards. When you draw these ray diagrams in your notes, what you probably want to do is draw them nice and large. Even though I am going to draw them by hand, if you want to use a ruler to reproduce them, by all means do so. Pause the film as you have to. Okay, so we construct first of all the ray diagram for a plane mirror in the following manner. Okay, this right here we'll just say is the floor, and then right here is a wall, and then we'll say that the mirrored surface is here, right on the inside surface, if you will, on the left-hand side of the diagram. Okay, and then we have an object, for example, a person, say, standing in front of the mirror. We always draw the object as an arrow because the arrow shows orientation. So let's say that right here is an object like so. Okay, the object is some distance away from the mirror. That's this distance here. This distance here is referred to as the object distance, and we label it as DO, like so. Okay, now imagine, for example, standing in front of the mirror in the morning. Okay, how many light rays are reflecting off of you from the ceiling lights, for example, above? Well, an infinite number of them. So then therefore, how many light rays do you actually have to draw to construct the image? Actually only two, but you have to choose the light rays carefully. So what I'm going to choose are two light rays that are reflecting off the top of the arrow, or the tip of the arrow, and then striking the mirror. So for example, let's say that right here is one of those light rays, like so, and it strikes the mirror right here. Now, perpendicular to the mirrored surface at that location, right there is the normal line. So right here on the diagram is the angle of incidence. And then therefore I have to reflect the light ray on the other side of the normal line at the exact same angle. That's once again the law of reflection. Therefore the reflected light ray has to look like this. So right here is the angle of reflection, and it's the same as the angle of incidence. And now I do this again with another randomly chosen light ray that is coming off the tip of the arrow, say like so. And then this light ray strikes the mirror right here at this location. This right here is the normal line at that location. Right here is the angle of incidence associated with this light ray. And then it undergoes the law of reflection. I reflect that light ray to the other side of the normal line, and I do so at the same angle. That then looks like this. So right here is the reflected angle, the same as the incident angle. Notice that these two reflections, here and here, are diverging from each other. These are diverging light rays. So then therefore, if your eye was back here somewhere and you were looking in this direction towards the mirror, you would see these two diverging light rays as if they were coming from somewhere behind the mirror. So take the two reflections here and here, these diverging light rays, and extend them back behind the mirror. That is like so. So this light ray looks like it's coming from this direction. This light ray looks like it's coming from this direction. And notice that the two light rays appear to be coming from this point. That point right there, then, therefore, is the image of the arrow that you see. And then if you do this process for all points along the arrow, you would then construct the image of the arrow here, like so. So when you look at the mirror, when you look at the object in the mirror, as we sometimes say, you then see the image as if the image is behind the mirror. This type of image is referred to as a virtual image. Okay, now let me go ahead and draw another line here, like so, and the image appears to be some distance behind the mirror. That's this distance here. This is referred to as the image distance, and it's called d sub I. So imagine, for example, standing, say, 5 feet in front of the mirror, and then you look at your image and you wave to yourself, and when you look at your image appears as if it's behind the mirror. How far away from the mirror does the image appear to be? Okay, well, in order to answer that question, we have to draw some additional lines here on this diagram. As you can see, this diagram is getting a little bit crowded, so as I said earlier, you want to make sure that you draw this nice and large, for example, in your notes. Okay, let me go ahead and draw a line in like so. Like this. And now take a look at these two angles here. Recall that these two angles here are the same thing. Specifically, take a look right here at the reflected angle. The reflected angle is the same as this angle here. Okay, now take a look at this black angle like so. Let me label it like this. This black angle is the complement of this incident angle. However, because this incident angle is the same thing as this angle here, this then means that this angle here on the diagram is also the complement of this red angle. Therefore, these two angles are the same. And then just take a look at this diagram. What we have here essentially are two right triangles. Right here is a right triangle, and right here is a right triangle. Notice that those two right triangles share the same angle. They're both right triangles, and they share right here the same side. Therefore, what could you say about those two triangles? They're pretty obviously congruent. So because they are congruent right triangles, what could you then say about the object distance and the image distance? Obviously, they're the same. Therefore, the object distance is equal to the image distance. So if you stand, for example, say 5 feet in front of a mirror, and you look at your image appears to be 5 feet behind the mirror. Okay, one other thing here in this basic derivation, the object itself here has some size. That size is referred to as HO, where typically the letter H stands for height. Right over here is the image. The image has a size. This is referred to as H sub I. By drawing another set, it's not necessary for me to do so, but by drawing another set of what are ultimately congruent right triangles, you could also show that HO and HR are the same thing. So if you're 6 feet tall and you're standing in front of the mirror, your image is also 6 feet tall. It's once again just another series of congruent right triangles on this diagram. Okay? Okay, now let's go ahead and take a look at today's lecture example. There's only one example for today involving a situation with a plane mirror. So take a moment to copy it down into your notes. I'll read it here on the screen. How tall must a vertical mirror be in order for a 6 foot tall person to see his or her entire length? How far above the floor must the mirror be positioned? We'll assume that the person's eyes are 4 inches below the top of his or her head. Okay, let me go ahead and draw this out. Okay, so here's the floor. Let's say right here is the mirrored surface, which is on the left-hand side of the diagram. And then we have the person, the object, the 6 foot tall person. I'm going to draw the arrow here as rather large, like so. Okay, so there's my object. And then this distance right here is the person's height. That's the object height, HO. That's given to us as 6 feet. Okay, now what's not given in the problem is how far away from the mirror the person is. That's the object distance. The object distance DO on this diagram is right here. Okay, and then let's say that right here are the person's eyes, like so. And then we have to have light rays coming from, first of all, the top of the person's head, and then secondly, the bottom of the person's foot, striking the mirror and then entering the person's eyes. This will then give us 2 sets of congruent right triangles. So first of all, for example, imagine the following. Imagine a light ray coming off the bottom of the person's foot and then striking the bottom of the mirror. At the very least, the following has to happen. So we have a light ray, for example, like so, striking the bottom of the mirror, which is right here on the diagram. And then that light ray undergoes the law of reflection, and it reflects into the person's eyes, like so. Okay, now, draw the normal line right here at this location, and then right here is the angle of incidence, right here is the angle of reflection. Remember, of course, that they're the same thing. So then therefore we have a right triangle here, and we have a right triangle here. They share the same side, they have the same angle, they're both right triangles, and then therefore they're congruent. This then means that this distance here is the same as this distance here. Let's refer to each of these as A. Okay, and then we get our second set of congruent right triangles by looking at a light ray that is coming off the tip of the person's head. So we have a light ray like so, coming off the tip of the person's head, and then striking right here at the very least at the top of the mirror. So then therefore on this diagram, the mirror is right here. Like so. We're supposed to calculate the size of the mirror and how far it is above the floor. Notice that the size of the mirror is less than the height of the person. Okay, now this incident light ray, I still have to reflect it. It undergoes the law of reflection right here at this point, and then therefore the reflected light ray goes like so, and it enters the person's eye. Okay, right here is the normal line that is perpendicular to the mirrored surface at that location. Right here is the angle of incidence. Right here is the angle of reflection. They're the same. Once again, we end up here. Let me go ahead and extend this. With another set here of what are obviously congruent right triangles. They share the same side, they're both right triangles, and they have the same angle. So then therefore, this distance here is the same as this distance here. Let's refer to those distances as B. Notice that 2B is given to us. That's the distance that the person's eyes are below the top of their head, 4 inches, which is 1/3 of a foot. So 2B is given to us as 1/3 of a foot. Okay, now let's go ahead and figure out what 2A is on the diagram. 2A is obviously HO minus 2B. So that's 6 feet minus 1/3 of a foot, which is 5 2/3. Like so. Okay, now stare at the diagram. What is it we're supposed to calculate? Well, take a look at the size of the mirror. Notice that the size of the mirror right here is actually nothing more than A plus B. So let's go ahead and find that distance. So the size of the mirror is A plus B. Well, 2A plus 2B is equal to HO. So then therefore now just divide by 2 to get A plus B. That's HO over 2. It's half the person's height. It's 3 feet. So for example, when you're standing in the bathroom here at school and you stare at the mirror on the wall, note the size of the mirror. The size of the mirror is not going to be equal to a typical person's height. Instead, it's roughly half the person's height. Okay, now what we want to do is we want to position the bottom of the mirror here such that the person is able to see their feet. Notice that the distance that the bottom of the mirror is above the floor is the distance A. So now what we have to do is we have to calculate what A is. So the distance above the floor is A. Well, to do so, let's go ahead and use this A plus B here for a moment. So A plus B is equal to 3 feet. So then therefore the distance A here is going to be 3 feet minus B. So we have to figure out what B is. Well, let's go up to here. Notice that 2B is equal to 1/3 of a foot. Remember, that's 4 inches. So then therefore the distance B is going to be 1/6 of a foot. So then therefore this is 3 minus 1/6 feet. So then therefore that's what? 2 5/6, whatever that is. Like so. So a little bit less than half of the person's height. That's the distance that we have to position the bottom of the mirror there above the floor. Notice what is not important in this calculation. Notice that the distance DO doesn't matter. It doesn't matter how far you are from the mirror. If the mirror has this size and it's positioned in this manner, you're always going to be able to see the image of your entire body. Now, this is usually not the case that you would see, for example, with a bathroom mirror, say here at the bathrooms at school. In general, what you will find is that the mirror itself is, yes, about half the size of a typical person, but it's positioned well above the floor such that you don't see your feet. Instead, you basically just see yourself from the waist up. And then it doesn't matter how far you are standing from the mirror itself, you're basically always going to be able to see yourself from the waist up. Okay, go ahead and pause the lecture right here, please, and then briefly take a look at the barbershop demonstration that I've posted for you in today's folder. The barbershop demonstration is a nice qualitative introduction to a mirror combination. So take a look at that demonstration video now. Okay, now that you've seen that demonstration in a qualitative manner, here's the basic description of what it was that you saw. This is the barbershop mirrors demonstration. Okay, now I'm not going to draw out the ray diagram associated with the barbershop mirrors demonstration. If you do, the ray diagram gets really complicated really fast. Instead, I'm going to give you the basic idea as to how a mirror combination works. Okay, so let's say that I have my two mirrors, like so, 1 and 2, and they're parallel to each other. Okay, and then I have my object. I'm just going to draw my object here as a point, and for simplicity, let's just put the object right in the middle, right in between the two mirrors, like so. And then we have light rays coming off of the object and then reflecting off of the mirrors. So let's see what happens first of all with the first mirror. Okay, right here is the object distance then for the first mirror. This then means that the reflection is going to be at the same distance behind the mirror. That is then therefore over here. So this right here is the first reflection for mirror number 1. Okay, now here's where it gets a little tricky. Where does that reflection form for the second mirror? Well, the basic idea behind a mirror combination is as follows. The image for the first mirror becomes the object for the second mirror. That means the following. So imagine a light ray coming from the object itself and reflecting off of mirror number 1 and then hitting mirror number 2. When that light ray hits mirror number 2, where does it look like it's coming from? It looks like it's coming from back here. So then therefore the image for the first mirror now has to be thought of as the object for the second mirror. So then therefore the image that forms for this object for the second mirror is then therefore here, like so. So this right here I'm going to refer to as the image from mirror number 1. But the same thing happens for a light ray, originally starting from the object and then striking mirror number 2. So now imagine a light ray coming from the object and then striking mirror number 2. Right here is the object distance. Therefore, the image distance is the same. It's this distance right here. So this right here is the first reflection for mirror number 2. However, That light ray that originally came from the object and reflected off of mirror number 2 then strikes mirror number 1. So where does that light ray look like it's coming from? It looks like it's coming from back here. So then therefore, the image for mirror number 2 has to now be thought of as the object for mirror number 1. Well, right here is the object distance. Therefore, the image distance is here. So this right here, just to kind of name things as I'm going here properly, is the image from mirror number 2. And so on and so on and so on. Notice that all of these images here are evenly spaced. So that's why you always see the same distances in the barbershop mirror demonstration. Once again, take a look at those distances in the short barbershop demonstration video that I've posted for you. You'll also notice that the images appear to kind of gray out as you move out towards infinity. The reason for that is because as the light just reflects back and forth between the mirrors, every time that the light reflects off the mirror, some of the light is absorbed. It's absorbed by the mirror surface itself, so therefore the brightness or the intensity of the light itself decreases the more reflections occur. So eventually the reflections dim out for that reason. Okay, that concludes today's lectures in today's folder. Today's t-shirt was skinless. Remember everybody, crush the curve.